Welcome to another tutorial. Today we'll be talking about transient diffusion. We will handle Dirichlet boundary conditions, but we will also look at cylindrical coordinates. And so the problem that we will be encountering today is a one-dimensional system. Instead of looking in the x direction for our discretization, we'll be looking in the radial direction. We have initially 300 degrees Kelvin everywhere, and then at time equals 0 we impose a Dirichlet boundary condition, a surface temperature of 500 K. And we'll assume this is stainless steel. Here's typical properties that you would find. We have a 1 centimeter radius in the radial direction, and with thermal conductivity, density, and heat capacity, we can calculate our thermal diffusivity, and with these numbers we get 4e to the minus 6. So that's a number we're going to need to use in our OpenFOAM. It's important to recognize that we have an analytical solution to this problem. It's an infinite series solution. The temperature distribution here, given in terms of theta, where theta is going to be the temperature at any location and any time, subtract 500 divided by the initial condition minus that new Dirichlet boundary condition. And the solution that is presented here is a simplified version of a more general solution, one where instead of a Dirichlet boundary condition, we are looking at a Robbins boundary condition, namely where at time equals 0 we have an imposed convection in terms of a heat transfer coefficient and a free stream temperature. And so if we take the limit of that and let our heat transfer coefficient go to infinity, then immediately what happens is the temperature, the free stream temperature, is imposed as a surface temperature. And so it's a small it's a subset, a simplified version of the more general solution. But you see there's some Bessel functions of the first kind, different orders, order 1, order 0, and the zeta here is unique for each root, and we find that from this expression here. We find the roots to this equation. And again, this will change once we consider a convection condition, a true Robbins boundary condition, but for the problem statement here, this is the simplified version of that analytical solution. And so we can plot this. We can look at this as a function of time and space. These contours, notice this is time on the y-axis, so these contours are in both space and time. And if we take traces at specific times, we can get temperature distributions at these different times. Here's 5 such times plotted in terms of our radial location. And so at r equals 0, we've got a symmetry boundary condition, and that's really what we want to do with this, is a one-dimensional analysis where we have take advantage of symmetry at the center, and we just need to discretize along R. So how do we do this in OpenFOAM? The boundary condition that we are going to take advantage of is called a wedge boundary condition. And what that means is I'm taking that cylinder and taking a wedge slice of it along the length of the cylinder. And so if there's ever a function or a boundary condition or something in OpenFOAM that you want to find more information on, you can just type foam info. In this case, we'll type wedge because it's the wedge boundary condition. And in this case, it found some items where the phrase wedge is found. And so this is going to be a wedge boundary condition. We're going to apply that to some patch. So this, in this case, option 1 is what we're looking for. And it prints out, it echoes back to the screen the information section of our .h file. And then it goes and looks for tutorials that contain this, in this case, wedge. And so here's 10 out of 18. As I looked through each of these, I found this incompressible moving cone one was one that was interesting to look at. So what we can do is go straight to that tutorial go to incompressible. It's a pimple foam solver, it's a laminar, and then this should just be moving cone. And what we're going to do is we're going to copy this entire directory, moving cone, to our home, and I have a pointer here that goes to another directory. And so as I go to that location, I now have a folder called moving cone, and as let's go to that location and let's run this and take a look at what okay, so we have a 0 folder, constant folder, system folder. It's titled moving cone, so there's going to be some extra physics in there that we're going to not necessarily care about. As I go into the 0 folder, it's obviously I have a U and so I have a velocity and a pressure. I don't have a temperature, and so I don't necessarily want to copy all of those. I don't need all of those. I'll copy a temperature over in just a minute, but there's another file called point motion. And this is the cone. This is a cone that's moving in the domain, and we want to look at velocities and pressures. And so I can go into the system folder. I can check, just make sure my solver. I know it's pimple foam, but if I was just given these case files, then I could look into the control dictionary, and I could see right here that this is a pimple foam solver. And so if I take everything as is, and I'm first going to need to go up a directory and then run my block mesh. Creates my mesh. I've got a number of patches there. It looks like 3, 6, 8 different patches. And then I just need to run the solver, which it is designed to run, which is pimple foam. And it's going through a bunch of iterations. It might have been wise for me to go back and change the time step or the total number of iterations that I'm considering, but suffice it to say, it's solving this tutorial as it's intended to be solved, as it was designed to be run. And I can create a file which now I can go into my ParaView and open up. And so you see here's the cone, and as I play this, the cone is moving. So there's some extra OpenFOAM knowledge that we're not going to focus on in this tutorial, but I did want to take just a look at the domain. So let's look at the domain, and as I rotate that around, you see that it is indeed a wedge type domain. And so the wedge boundary condition, again, is what OpenFOAM is going to use to impose an axisymmetric model. And so what I thought we'd do is just dive into the block mesh dictionary file here and just take a look at what's being called out, what's being created. So here's my block mesh dictionary file. I'm converting, looks like this is in millimeters. I've got a number of points here. Looks like I got 20 different points. And this is the XYZ location of those points, point 0, 1, 2, all the way to point 19. And then I'm creating some blocks. It looks like I have 5 blocks. And then I look at my patches, my boundaries that I established, 1, 2, 3, 4, 5, 6, 7, 8. And so this is if we look at the title of these, we have moving wall, far field moving, fixed wall, axis, left, far field, back, and front. So if we go to the ParaView, then we can go in here and we can look at, let's take a look at what the far field is. So the far field is just those top slices there. If I include far field moving, then I get that other patch. This is the region of the cone that is moving down. I can look at my left and I can look at my front and then back. Let's take left off for a minute. So my front and my back are those surfaces which are the wedges. And so not surprisingly, as I go to the dictionary file, I see that the front and the back, the type here is wedge. And there's a number of surfaces that are going to be defined in that same surface called back, far field, left, axis, fixed wall. So let's, as we number these, we look at the points here. So I've got some x locations. I got negative 7.5, negative 7, negative 3.5, and 0. What that is doing is it's along the axis. My y and my z were 0, and y is the radial direction. So that's 0.0, 1, 2, and 3. And then as I look at the rest of these, 4, 5, 6, 7, all the way to 19, I can map these out according to the schematic that we're looking at here. And then as I go and I look at the blocks that are being created, let's take this one as an example, 0, 1, 5, 4. So I have 0, 1, 5, 4, that's on the back side. And then I go 0, 1, 13, 12, 0, 1, 13, 12. So that block is the wedge that's closest to my axis. And you'll notice that as I create the rest of these, I've got a block here, I've got a block here, there's 2, and then I have 3, 4, and then 5. And those are my 5 blocks. And now as I go to the boundaries, let's look at the moving wall. 1, 5, 13, and 1. 1, 5, 13, and 1. So the moving wall is going to be this little slice here, and I can prove that here. I should get this little slice here for my moving wall. So here's 1, 2, and 3, which contain my definition of my moving walls. And so my moving wall is that little slice there, and then 5, 6, 14, 13. 5, 6, 14, 13, that's that slice there, and then I've got this third one here, which is going to be 2, 14, 6, and 2. But it doesn't matter the order. And then far field moving is going to be these guys up here, this one here, 9, 17, 8, 10, 9, 17, 8, 10. And then I've got the fixed wall, 3, 7, 5, 15, 3, 3, 7, 15, 3. So that's that little slice there. And then in addition to that, I've got this other one up here, which is going to be 7, 11, 19, 7, 11, 19, 15. And notice the order that these are called out in each case are if I do a right-hand rule and the order that they're called out, I am left with a vector that's pointing out normal away from the domain. So we can go through all these, but really the ones we wanted to focus on here were the ones with the wedge, and then along with wedge we need 2 callouts for wedge, and we need something that's called axis. Where's my axis? Oh, not called axis. I'm going to have something that is labeled axis, but it's going to be empty. And notice these surfaces here and here are also going to be empty. In other words, the only direction, in this case I've got a 2-dimensional domain, but for us in this problem it's much simpler than this. I just have 6 nodes, 6 points, and I can create those with functions r, and I'm going to create a 5-degree wedge here, so half of that angle is going to be 2.5 degrees. And so my z value at point 2 is going to be negative r tan of 2.5, and then my point 4 will be positive r of tangent of 2.5 degrees. And so with these 6 points, I have my entire domain. So I can change these. I just need 6 points. And the first one is going to be some factor f, and it really doesn't matter what I choose because I'm only going to have one mesh element in that direction and one mesh element in the wedge direction, in the z direction. And it's in the radial direction I want to discretize, so I'll have 50 or so elements there. And so I want to be able to eventually, at the end of this tutorial, I want to be able to do some parametric studies. I want to say, well, what if R was something else? And I want to be able just to change that and run it without having to recalculate everything. And so the way that we do that is to declare the variables. And so let's let f equal 1, and then R, I'm going to convert this to centimeters because my radius is centimeters. And so that will be R there. And then I'm going to do something called a half angle, and that'll be 2.5. And we'll list it in units of degrees, knowing that when we do the calculation, we'll change that to radians. And so I'm going to do some calculations here. And when I do calculations, I'm going to call this z of the in the positive direction, and we'll call out the calculator #CALC, and then we put the equation in parentheses, or not in parentheses, in quotation marks followed by a semicolon. And so my positive ZP is going to be R, and whenever I call out a variable, I need to put a $sign in front of it, times the tangent of my half angle, and that's in units of degrees, so I will multiply that by pi 1.14159, and we'll add a few more decimal places there, divided by 180. So that's going to give me another variable called ZP, which is Z in the positive direction, and Z in the negative direction is going to be another calculation. And that calculation, it's be a semicolon, that calculation will just be -1 times Z positive. And then the other one is going to be FR. We'll call this FR. And that is just going to be equal to -1 times my f variable that I have multiplied by my radius. So now I've got these variables, ZP, ZN, and FR, and when I go to my vertices, I can just mimic this table here. This is my point 0, 1, 2, 3, 4, 5. And so for my 0, I will just have that, I need to put a $sign, FR, 0, 0. This one will be 0, 0, 0. This one will also be FR. And in this case, we'll come up to the value of R in the Y direction, and then we'll have a Z negative for 0.012. And the next one down, we'll have a 0 in the X, and the Y again will go to R. And then this will also be Z negative. And then the final 2 points, this will be FR again, and my Y will be radius, and now these two will be Z positive. And we'll do the same thing, except to have a 0.0 for my X. Okay, so what we're doing is we're enabling a future parameterization study of these different factors. And now we go to the blocks. I only need one block. I don't need all 5 of these. And as I go back to the order of my points, I want this to be 0, 1, 3, 2, followed by 0, 1, 5, 4. And those are going to be my 8 points. 0, 1, 3, 2, and then 0, 1, 5, 4. And in this case, in the x direction, I only want to have one element. In the y direction is where I want to have all the discretization, and then I have one in the z direction. And we'll keep this as a simple grading, that's fine. Okay, now on to the edges. Let's take this one. We don't have a moving wall. Let's call this one just the surface. So this is going to be this surface here. That's where my surface temperature is going to be imposed. And so I'll map this, I'll put the order of this such that my right-hand rule gives me a vector pointing out. So 2, 4, 5, 3. I only need one of those there. 2, 4, 5, 3. And we don't have any of these. I'm going to have an axis. Let's just delete those out of there. My axis will be type empty, just like the tutorial was, but I only need this top one. I only need the 0, 1, 1, 0. That is my axis there. Okay, then instead of left and far field, in fact, let's take this one out. We'll have a back and a front, but let's call this one front back. And this will be type empty as well. This is my z direction, or my x direction. And so what are my faces there? I want to have these two faces here. I want to have 0, 4, 2, 0. And 1, 3, 1, and to get it pointed out, I'll have 0 or 1, 3, 5, 1. So it'll be 0, 4, 2, 0, and 1, 3, 5, 1. So that is my front and back. So that's going to be this surface and that surface. Now I've got my 2 wedges, and I'm only going to have one surface in there, and we'll need to modify it obviously, but so let's look at the wedge here. This side here is going to be 0, 2, 3, 1. That's for my one side. We'll call this wedge back, and we'll call this one wedge front. And this was 0, 2, 3, 1. That's my wedge back, and then my wedge front will be 0, 1, 5, 4. Okay, so I think we have that all set up now, and then we merge them together. So our block mesh dictionary should be fine. I changed this to be centimeters so that I can just use R of 1 in that case. And that should do us. We should be able to go back. Actually, let's rename this from moving cone. We'll call this transient diffusion wedge 1. So we'll save wedge 2 for Robin's boundary condition. So inside of here now, I should be able to, well, let me delete all these. We don't need the post-processing. And then in the constant, let's get rid of the poly mesh. We're not going to need momentum transport. dynamic mesh dictionary. Going into my 0 folder, I can get rid of all these, and we'll copy actually let's leave velocity in there for a minute. Got transport properties, and notice because this was a Navier-Stokes type problem, we had viscosity in there. We want thermal diffusivity. We'll change that in just a minute. Okay, so here's my block mesh dictionary, and I should be able to now come in here and run my block mesh. And this first part is because I have some calculations being done. We've got some errors here. Let's go take a look at that. It's not recognizing R. It's not recognizing half angle. And let's go to our block mesh dictionary. No, it's because we didn't put semicolons there. Let's resave that, and then we'll come back to Ubuntu, and let's see if we can run this again. So we still have an error. We've got ZP that's not declared. We're probably missing a $sign. If we want to go back and look specifically what line it's referring to, it's line 17. 17 is where we start all the callouts, but if we look closely, I've got ZP, I've got a $sign there, I've got a $sign there. I didn't have a $sign here. And I've got $signs all down here, so let's see if that fixed our problem. Good. So now we've got 50 cells. We've got 5 different patches, different labels. We've got surface, we've got axis, we got front back, which is both front and back together. Then we got the 2 wedges, our wedge back and our wedge front. So let's go into pair view and just make sure this looks like we expect it to look. And that looks good. We've got our 50 divisions in this direction, and we've got our wedge. Let's go back and look at the front back. That's the front back. We've got the wedge back, which should be that surface. Let's get rid of front back. And then we've got wedge front, which is that surface. Those are our 2 wedges. And then we've got surface, which is this top one. And there's only one element there, because again, my divisions are going to be in the Y direction, which is my radial direction. Okay, so I have a block mesh created. Now I just need to go and change some of the other files. I don't need my cutting plane. I need these other ones here. I'm going to need to change my control dictionary file from pimple foam to Laplacian foam. Actually, let's, just to be on the safe side, what we're going to do is we're going to copy over a Laplacian foam control dictionary file. We'll do that for all 3 of these actually. We'll copy these 3 over, and then I'm going to copy over a transport property file as well. So let's go back to our tutorials. And those were in basic, Laplacian foam. That's the flange. And there's my folders, so I'm going to copy 0T. I'm going to copy that to my home directory. Actually, let's just copy it there, and then I'll move them over in just a minute. Okay, so we got the temperature file. We want to go in the constant folder and look up the transport properties, copy that over. And then we want to go into the system folder and copy over the control dictionary file. We want to copy over the FV solution and the FV schemes. So I've got those 5 now copied over. Let's go take a look. So we'll take these 3 and we'll move them into the system folder. And then we'll take the temperature and move it into the 0 folder. I'm just going to get rid of the velocity there. And then I'm going to take the transport properties and we're going to copy that into the constant folder. Okay, so let's go now. This is now, everything is designed to be tied to Laplacian foam, and that's what I was looking to do here. So this now is my diffusivity. If we go back to our definitions, this should be 4e to the minus 6, so we need to update that. We're done with that, and now we're actually done with the block mesh dictionary as well. And then we'll go here into the 0 folder and look at the temperature file. The temperature file has the internal field of 273. We are going to change that to 300. And we've got to update these patches to be reflective of what we did in the block mesh dictionary, where we have surface, axis, front, back, wedge front. Those are our 5. So let's come to our temperature file. We're going to have uniform 300. That's our initial condition as described by the problem statement. Our first patch was called surface, and this now is going to be a Dirichlet boundary condition, so a fixed value and a value of 500. Again, according to the problem statement, the next one's called axis, and that was the value type was empty. The next patch we called front back. That was also type empty. And the next patch was called wedge back. And in this case, we just need to make it type wedge. And then we'll do the same thing here for another patch called wedge front. And that also is just type wedge. So that should be good for our temperature file. And the last thing we'll do is go take a look at the control dictionary file. It's going to run the Laplacian foam. We want to go to, let's go to 10 seconds. We can get away with smaller delta t. I want to save every half a second, so I should have 20 files or 20 folders once I get done with this. I'm going to change the write precision to 7 and the time precision to 7. So we save that, and now we should be able to come in, and we've got to change directories back to the this is transient diffusion wedge. So we've got our block mesh created, and now we can just type Laplacian foam. And it goes through there. I'm going to I'm going to go back to my control dictionary file actually and change this to go back to another smaller order of magnitude with the time stepping. Run this again. We got to go remove all the files. And this dynamic code folder is what's generated because I have that calculator utility in a couple files, or at least in one file at this time. So I'll run OpenFOAM. It's going to run through that. And I have saved every half a second, and I've got something called foam.foam already, so I don't need to create that, but I can go into my pair view and open this up. And now we should have temperature built in there, and we've got, as we play this through, we can see the temperature bleeding through. If time goes to infinity, we expect the whole thing to be 500. And so we're not quite there yet. But that's kind of a brief tutorial on how to handle the wedge boundary condition. And so we want to now take a look at, we can extract data from the center line there and compare just to prove that this is calculating it like we think it is at these specific time stamps. And compared to there, we have some small amount of error. Here's the norm of those error vectors. But really, what we want to do is in this case, we want to do a batch calculator, and we want to consider input uncertainty. So in other words, this very simple problem, which has an analytical solution, we're going to pretend like it doesn't have an analytical solution. And we're going to assume that we have some data that we're dialing in all these numbers here based on data that an experimentalist gave us. They measured the temperature at the initial temperature and the surface temperature that was imposed at time equals 0. That was 300 and 500. They measured K. They measured density. All these parameters that we have to dial in to our simulation. It's important for us to recognize that none of those are perfect. They all have some uncertainty with them. And so if we take each of these, and we'll assume we got these from the experimentalist as well, our temperatures were measured with a 1 degree error, and all these call outs for each of the other parameters. So we've got 1, 2, 3, 4, 5, 6. We've got 6 input parameters, but in reality we only have 4 because these 3 get combined into a single parameter known as the diffusivity. And so what I want to do is I want to calculate my input uncertainty, and that's done by looking at this sensitivity coefficient, and then the product of that and my input uncertainty for that particular parameter, for that particular input, and it's the square root of the sum of the squares of those products. And this is a partial derivative, but I'm going to approximate that as a forward difference, finite difference approach there. And so S represents some parameter that I care about. Maybe it's the temperature at the center line at a specific time. And so that's what S represents. And so I'll calculate this sensitivity coefficient by considering multiple simulations and data from those multiple simulations. And so if I'm looking at the influence of one input and parameter, my TI, then I would change TI by some amount, evaluate that, find out what my centerline temperature is at a specific time, and then compare that to my base case, which is all these numbers. Take the difference between those, that's my DS, and then in the denominator that represents how much I decided to step it by when I considered that new case. And so I'm going to just use the uncertainty as that delta x in each case. And so I'm going to take case 1. Case 0 is going to be my base case. Case 1 is going to consider an initial temperature of 301 instead of 300. And then case 2, we'll go back to the base case values for TI, and we'll only change TS. And then we'll only change alpha, and then we will only change R. By the way, this alpha number comes from looking at the equation of alpha and doing something similar for this, looking at the propagation of uncertainty. There's three parameters that I use to calculate alpha: K, rho, and CP. And I just need to look at the partial derivative of that with respect to each of those, multiplied by their uncertainties, square root of the sum of the squares. And if I carry that out, I get this value here for my uncertainty. And so you see I've added that to my nominal value for alpha, which is right here. And so I have 5 cases total. I've got my base case, which will be case 0, and then I've got case 1, 2, 3, and 4. And what I really want to do is I want to create some script that knows, right? It can go into this file as an example and then update this number. If I can just tell it to update that for case, can't remember what case it was, case 4, from a value of 1 to a value of 1.05, then I can automate this. And for this example, there's only 4 extra cases. This could be done by hand with reasonably little effort. But when we get into other kind of batch calculation needs, then I could have 50, maybe 100 different simulations that I want to run. And I don't want to have to keep opening up the block mesh dictionary file and changing it to something, and opening up the T file and changing it. And so I've got 3 different files I need to access. I got the temperature file, which is where which was where the TI is stored and where TS is stored. And then if I want to change alpha, I need to go in the transport properties file. And then if I want to change R, I need to go in the block mesh file, the block mesh dictionary file, actually. So the way to do that, one way to do that, is to create a script in standard Unix programming language that is calling out all these things. And in order to do that, first we're going to create a file that includes all of our case values. So for case 0, those are my base values. I don't need to change anything there. For case 1, I'm only changing TI. Everything else is base value. In case 2, I'm only changing TS. Case 3, I'm only changing alpha. In case 4, I'm only changing that. And so I'm going to take these 5 by 420 different values, and I'm going to list them in order in a single column format. And then I'm going to create this script. And it's shown here. I'm not going to go into all the details on the programming, but this first line is taking a file that I'm calling test cases, which has all these 20 data points in them, and I'm going to load that into a variable called rtext. And then I'm going to step from 0 to 4, so that's 5 different scenarios. 0 to 4, I have 4 cases, with case 0 being using the nominal values. And then I can type in commands that I would use in a regular Ubuntu environment. And so I want to take this folder and I want to copy it in its entirety. I'm going to go back and I'm going to get rid of the polymesh. I'm going to get rid of everything, so it's just the fundamental bare bones case files. And so I'm going to copy that bare bones version and I'm going to rename it case, but then I use this $i, which is going to step through 0 through 4. And so at this point I will have created a new folder called case 0 for the first loop through here, and then I'm going to change directories into that folder, and then I'm going to change directories into the 0 folder. And this sed command, the sed command, is a stream editor, and so it's looking for in this file T, it's looking for a phrase that is uniform space 300, and I'm going to replace that with uniform, and I'm going to call out my R text, and in this case I want the very first loop with I equals 0, I want it to be element 0. I want it to be 300. But the next loop through, when I equals 1, I want it to be 0, 1, 2, 3, 4. I want it to be the fourth element, and then plus 4 more, and so on and so forth. And so I can step through that with this I, according to this call out here. So I want to replace TI, and notice that sometimes I'm just going to replace 300 with the value 300. But this test case, the way it's written, is just going to automatically, when it's 300, it'll give me 300. When it's 301, it'll give me 301. And then I also want to replace, for the surface temperature, since I have that new boundary condition, I want to look for the phrase 500, and I want to replace that with something from that R text vector, and it's going to be element 4 times I plus 1. Whatever this one was, I want to take the next one. And so for I equals 0, it's the first element. For I equals 1, it's the fifth element. And then I want to change directories up a level, and then I want to go into the constant folder, and then I want to do the same thing for alpha. And then I want to replace the string 4e to the minus 06 with the next element in my test cases vector, in that R text vector. And then I want to go back up a level and then go into my system folder, and I want to do the same thing for radius. So I've got my 4 parameters, my TI, my TS, my alpha, and then radius. And so I want to look for, in that case, I want to look for something that is R space 1, and I want to replace that with R space the final element in that vector. So this test case vector is again organized by groups of 4, and those represent my 4 values that I want to input there. So once I do that, I go back up a directory, and then I run my block mesh utility, and I don't want it to echo back to the screen, so I store that printout that I would normally get into a log file. I'll call that log.blockmesh, and then I want to run the Laplacian foam solver, and I'll store that output in a different log.Laplacian And then I'll create my foam file there, and I'll change directories back up so that the next time I go to I equals 1, the next loop, I can do the same thing, and I don't need to worry about locations of files or anything like that. So this will loop through that and it should give me a folder called case 0, a folder called case 1, 2, 3, and 4. And in those, we'll go look at these. You'll see that depending on the case callouts, I'll have an updated number there. But a few things I need to do first is to delete all of these from here, because I don't want to copy all of that. All that is in my 0 folder is my temperature. Because my mesh is going to change, because the R is going to change, I want to, and in my script I have the block mesh utility running each time. So I want to delete that, delete this, and in the system, that should be good. And so this is my bare bones content that I have. And so if I take this is the script that I just had in the slides, and we should be ready to go. So all we need to do is come back in here, and because that script is in this location, then I just need to type bash wedge 1 batch.sh, which is the name of the file, and looks like we're having some errors here. What did I do? Oh, I don't have test cases. That's what I got to do. I need a file in here called test cases. So you see, it's going through and it's creating files there, but it's not doing anything in the folders because I didn't have that test case. And so we'll wait for this to get done and rerun this after deleting these 4. Okay, so now I've got my .sh file. I'm going to run the bash on that, and then I've got my test cases file in there as well. So that should work. Yeah. And so now is it starting to create this? I've got the 0 folder, and I've got all my processed files in there. I've got in my console. Let's see. So this one was changing the T infinity. So if I come in here and I look at this, oh no, this was my base case. Case 0 is my base case. Case 1, I should come in here and find that my temperature has been updated to 301, while this one is left at 305. And then if I go into case 2, I should see that my temperature here changed to 501, and this one went back to 300. So I've got all 5 cases run, and it's saved the data in there, and I could have changed the bare bones version of this, which again is right here. I can change that in the system if I wanted to change how much I save. Maybe there's only like 2 or 3 time steps I really care about. If I'm doing some study where I'm actually going to compare 2 experiments eventually, then there's likely only 1 or 2 time steps that I might care about. So this is gonna bog down my system quite quickly if I have 100 or such files that on my system, folders that I wanted to run, simulations I wanted to run. Okay, so now I can go in. I've got 5 sets of results, and I can go load them in ParaView. Oops. And really, what I want to do is do a line plot that's in the center of the y-axis, which is my radial direction. And I want to take a look at that. I want to get rid of the gradients. I don't care about the gradients. So there's my temperature, and as I go through that, I can see it rising up slowly in the center. As we would expect, eventually that new boundary condition bleeds over into the center, so at time equals 0.5 seconds, this very center of the rod has not felt the effects of my new boundary condition, but by 1 second you can see that it's already started to see that, to feel the effect of that. Now I'm at 300.8, and then it just continues to rise after that. So let's say I wanted to save this profile for each and every one of those. And again, I've only got 5 of them. It's not the end of the world. It's not going to be too much of effort on my part to have to do that manually. But if I had more than 1 or more than 20 to 50, then it's something I don't want to have to open up each time and save. And so assuming I want to take that data and save for every time step, let's say, then in ParaView there's something called a trace, and this is similar to recording a macro in other softwares. But if I start this trace, let's show the incremental trace so that we can what's going to happen is this is going to build me a Python script, and I'll be able to run that in like in a DOS environment or a command window in Windows, and it'll take all the results that now exist in all these folders and just save the data as I want it saved. So I click on OK, and there's no window you see, but as soon as I hit open and I go to this case 0, you can see a new window pop up, and that is my Python script generator. And so you can see here that it's going to open up a file from case 0 called foam.foam. It's going to create an internal mesh by default, and it's got these by default. We can change these later, but so right now I just want to create this script. And what I want to do is hit apply so it appears, and you see some additional Python script has shown up. And then I want to do a line plot on the y-axis. And then I want to go and save this data. Maybe I want a CSV file. And let's call this line trace. And let's assume that we want to keep that for all the time steps, so all 20 time steps. And in here, I only want temperature. Let's change this to 7. I hit OK. And more of my Python script has been generated. And then I can stop my trace, because that's really the tasks that I wanted done. And so now I can save this file. We'll just call this line trace Python. So after we save that, now we just need to open up a command window in Windows, and we need to navigate to we need to navigate to the location where Parametric is installed. There is a Python executable function that we can make use of that then just calls that Python script that we just generated. So this is going to be in program files. We've got Parametric, that's what it is. Parametric. And within there should be a bin folder, and there is. This is where that executable needs to be run. And to run this, the executable name is pvpython, Parametric Python. And then we just need to tell that executable where this is located. And in this case, this is just OpenFOAM, and yeah, that's where it's located. But then I need to call out the file, which is line trace Python. py. And it takes just a few seconds to run, and what it's doing is it's going through and saving all those time files. And so if I come back and I look at that Python script, it's opening case 0. The other thing you want to be mindful of, this always doesn't get translated in, I've noticed, when you correct it to be the Y direction, or the y-axis. So go to your Parametric and just, since we force this to be y-axis, then now we can look at the points and just make sure these points are exactly what's located in here. And then this often doesn't get translated over for some reason either. Just make sure you have that line in there. so that the default is 1000, I think, and you want to be in line with more or less the mesh resolution. So 50 elements, I got 50 points there. And so we can go into case 0, and we can see all these CSV files created, and just to prove that this is working like we think it is, let's go run this script again, and we should see all those appear again. We'll double click one of these just to make sure it's what we believe it is to be. There's 50 points, starts at 300 and some change and goes up to 500. And then this here, this column is my y. So my x, my y, and my z. So I've got all those traces, and I can do the same thing for case 1. And down here where we save the files, the CSV files, I need to change that to case 1 as well. And save that. Go run the script again. And to the interested programmer in Python, I'll leave it up to you to modify this to be able to step through all of those. So in this case, we're just doing it manually, but you can quite easily go tweak the code there. So case 0, here's case 1. I've got all those. Notice I don't have anything for case 2 yet. I don't have those CSV files. But I can run through this and generate those for all of my folders. And then I can calculate my input uncertainty. So if we go through this exercise, let's assume that for whatever reason the centerline temperature, so R equals 0, and at 4 seconds is important to us in this hypothetical situation. We're going to call that TQ, and that's our quantity of interest. And so the uncertainty of that based on the input uncertainty is going to be found via this equation. We've got 4 inputs, so there's going to be 4 terms in this series, and we're going to approximate the partial derivative as a forward difference expression. We've got TQ. This will be case 1 because that's when we change TI. This will be case 2 because that's when we change TS. This will be case 3, that's when we changed alpha, and case 4 is when we changed R. And so in each case we're going to subtract from that value the value of TQ, and in the base case, so case 0. And for our example, the uncertainty is exactly what we used as the step, and so these are going to get canceled out in this example only, but so we'll be left with something like this. And if you carry that through, you go pick off that temperature in each of those files. I think this will be the 7th time step or so at 4 seconds, and then you'll find out that you get a temperature reading of 374.6. This is found from our case 0. Those are our nominal values, plus or minus the uncertainty, which if you carry out through these numbers, you should find 11.2. The analytical model could also be used for this, including a bunch of terms in that infinite series solution, and you find that that's 11.3. So we are awfully close. We get 374.6 plus or minus 11.2. And that, it's worth noting that we can look at each of these underneath this radical and find out which one, if any, is the significant contributor. In this case, it's my radius, just because I've gone through the numbers and I've seen that this term here by far dominates everything else. And so these 3 are small compared to this one. And so if this was a real situation and we weren't happy with that 11.2 as our uncertainty, then we'd go back to the experimentalist and we'd say, listen, there's this one measurement that is just throwing everything off and making it difficult for us to actually get reliable, trustworthy results from a simulation standpoint, a validation standpoint. Is there any way we can change that sensor? Can we buy a new sensor that is more accurate? Can we calibrate that sensor? But this is kind of the back and forth that one would encounter with between a computational effort and an experimental effort. Okay, that wraps up this tutorial, and the next tutorial we'll look at Robin's boundary conditions on this same geometry. Thanks.